Okay. Yeah, let's leave it like this for the moment. So I decided to now go into the SPM table because it's, first of all, I was in the flow of working on that because we just went over all of the distributions. And of course, these distributions that we discussed, they form the basis for what is in the SPM table. What we have not discussed, but what we will discuss next time, is the whole problem of multiple testing and why some of these p-values that we will discuss today are actually referred to as family-wise error-corrected p-values, which is kind of a weird denomination, but that's the denomination that's being used. So today we will clarify, given the theory that we have developed over the last couple of sessions, what and how these p-values and these probabilities in the SPM table are evaluated. But we will not, for all of them, completely clarify why they are evaluated in the sense of why they actually relate to some family-wise error-corrected measure of p-value. But these are actually two separate things. So one thing is what is printed into the SPM table, and the other thing is why can this be interpreted like a family-wise error-corrected p-value. And we will do the latter in the next session, and then the session after that. And today we will establish what is actually printed into this table. And before we go into that, I want to remind you of what we are actually talking about all the time. So I brought up SPM again, and now also finally printed the SPM table into your handout so that you always know what we are talking about. So this is very much of what we also did in the very beginning. So there has been a GLM formulated for each voxel, and a contrast has been evaluated. And then the final thing in such a GLM-based fMRI analysis is to evaluate the probabilities of peak statistics and cluster statistics and set level statistics using the SPM table. And I just want to remind you of what this entails and how you do it. So today I'm going to do it with the batch, as you now also are familiar with from the other course. So this is really, so if you, so the last time I showed you that we did it basically manually by entering things into the results, but of course also this you can automate and write a script using the batch editor, as we will then also continue today in the other course. And in this case, it's the results report. So you have to select an SPM, which contains pointers to the files that relate to that. And then for a given contrast, which has been specified, so here this is checkerboard data and it's the contrast both checkerboard versus baseline. You have to specify in this case the index of the contrast. There's only one. And then, and this is the more important thing, is you have to, as you do, if you do it the other way, you have to specify a threshold type. What this means in some more detail I will explain in a second. Let's choose none here. You have to define a threshold where the current recommendation is to use this. We'll also discuss that in a little bit more detail in a second. And you can define an extent threshold. Let's also do that. What that means we will also clarify in a second. And then you're basically ready to run. And you can of course save this as a script. And if you run it, it does its thing. And then you get to the SPM table. And of course this is what we're discussing all the time. So we are interested in this thing down here. Where you see at least three groups of things: set level, P and C. So the P values that I'm always referring are these P. So so this P here. Then at the cluster, or then there's another group called cluster level, where we have a P family-wise error corrected, and we have a P uncorrected. So we talk about this one, also about this K here. We're not talking about the Q for false discovery rate correction, as I said also in the very beginning. So we're not dealing with false discovery correction at all in this course. And then you have the third thing, peak level, with again a p-value family-wise error corrected, a t-value, which is actually the t-value that is if you click on it, you get the cursor goes to this voxel, and this is actually the t-value that is encoded in the statistic parametric map at that location. You get an equivalent z value, which you don't really need, and you get a uncorrected p-value. So we want to discuss these p-values, and these are just the MNI coordinates, which we will not discuss. There's also some more information down here talking about the Haight threshold, and some of the things that we've discussed, like the expected number of clusters, expected voxels per clusters, the full width half maximum estimate of the smoothness, and the Riesel volume for the whole thing. So at this point I have actually essentially rewritten the code that does this table, so I'm really clear about this. I also at one point started rewriting this code for this footer here. I'm not fully done with it, so I will not go into much details about this, but these are all quantities that of course are required for this. In the paper you then also find, maybe then also a little bit later in your script, something about this. Yeah. So this is what we are talking about, and this is actually very important because in every paper that uses SPM for data analysis or FSL, what is reported is essentially this table, but usually it's actually not this table directly, but it's some read off of this table with some personal interpretation of what these things might mean. So I'm also guilty of that. Because it's not really clear what these things mean, then people write what they think what this means, but then they copy this into their own table. So it might actually be less confusing if people would just take a screenshot and put this into the paper, but that then also looks a little bit cheap, and then the reviewer will say, "Ooh, this is just a screenshot. Doesn't look that nice." Good, so this is what we're talking about, and this is what we are going to do now. Good, so then let's leave SPM for the moment and go to theory. So I call this session the SPM 12, and then I put the version number into brackets, p-value table. So although I put the version number into brackets there, it's not that version dependent. Actually, what's in the SPM p-value table, this has been stable, I think, for the last 18 years or so, 16 years maybe. Maybe since SPM2, not much has changed there. So although I'm making the version number explicit here, you shouldn't think that it changes with every subversion of SPM12, but I wanted to make it very specific because I will include the SPM version with the paper, and then it's this SPM version and not some other SPM version. Last time, and this was also, I think, the last active participation or study question, we discussed this random variable q k larger than q larger than k u, and as evil as I am, I made a change since last time because I decided I don't want to call it q, I want to call it c. And the reason for that is that we have this other random variable, which is called CU, which models the number of clusters in an excursion set defined by the threshold or cluster forming value U. And when I named it Q, I wanted to make clear that this is a new random variable. This is very important, and I think I made that point. But now I decided that because it's of course similar to this, it's also about a number of clusters in the excursion set, but it has this second condition, namely the number of clusters within an excursion set defined by the threshold U, which have a volume larger than K. I decided in generalization of this, just the number of clusters, I call it C, because then it's maybe even clearer what it relates to. Yeah, so don't be confused. What was Q last time is now C, and I should have changed that also in the script. I think I just realized this morning in the script there's sometimes in the section before this there's still the little U missing for this at some occasion, but yeah, as the course proceeds there will be less and less typos. Okay, so the last, so I hope you guys prepared also the other study questions. So there was, and this maybe was something I can ask you, there was this question, what does something like this mean? So how do you read that? Agnesa. C is Q. So it was the last question in where it was called Q.
So the probability of Q being larger than not sure what Poisson.
Yeah, that's the cluster volume.
Okay, so the cluster volume has to be larger than 10, and is that a U or a 10?
That's a U.
That's a U. That's the cluster, number of clusters.
Yeah, any other suggestions?
I'm not sure. It represents the probability that the number of clusters in an excursion set is set defined by the value 3 with a volume larger or equal to 10 equals 2.
Yeah, I think it was 2 there. Here I just wrote 4, but yeah. Yeah, and then it went on. I think in the question it said something like this. I think.
So yeah. So this probability is less or equals 0.
Yeah. So I think the most tricky thing about this whole thing, so you all know what a random variable is. We did that last term. The tricky thing here is actually to get from the mathematical formulation to the correct interpretation, which I tried by spelling it out a lot, but one needs to get a little bit fluid in that. So you always should think about first what the random variable models, and then just read what this means. So the random variable, this C, let's put that here, this C larger than KU, this random variable models the number of clusters. So it takes on values that are numbers of clusters. So for example, 0, 1, 2, 3, and so on. So it's a cluster number, because there can be 4 clusters, let's say, in an excursion set. It's the number of clusters in an excursion set. Defined by U. Which is also called the cluster defining or cluster forming threshold. So let's call it CFT. The number of clusters in an excursion set defined by U, which have a volume equal to or larger than 3. Okay, why do I say 3? Yeah, and this is something, there's nothing to understand about this. This is something to memorize. That's a definition. So this random variable C subscript larger than K, comma U models, because random variables always model things, because probability theory is a model of the world. This random variable models the number of clusters in an excursion set defined by U. So this U is just there to remind you that the number of clusters in an excursion set, of course, depends on this cluster forming threshold. So the number of clusters in an excursion set defined by U, which is the cluster forming threshold, which have a volume equal to or larger than K. Yeah, so and this is why it's now also called C. So this used to be just the number of clusters within an excursion set defined by U. And this new random variable C, which is not new because we talked about it last week, this random variable C larger than KU is the number of clusters in an excursion set defined by U, which have a volume equal to or larger than K. Yeah? And this you just need to memorize, and then these kind of expressions make sense. So this is the probability that the number of clusters within an excursion set with cluster forming threshold 3 that have a volume larger or equal to 10 equals 4. So that's the probability that this random variable takes on the value 4 is smaller than 0.05. Yeah? Just need to get that into your system. Does anyone remember how this random variable C larger than K, comma U was distributed? You're just guessing. No, normal distributions, that was 2017. 2018, it's all about Poisson distributions. So what we learned last time, so we, except for Agnesa, was that C is distributed according to a Poisson distribution. And a Poisson distribution has this parameter lambda, which I also call lambda C larger than KU, because it relates to this random variable. From knowing that, if you know what a Poisson distribution is and how its probability mass function looks like, which is also, of course, in your script, and you should also memorize, you know that there's a typo in 7.2, and there's a comma too many. You know that the general Poisson, what's the general expression for the Poisson probability mass function? So if you have something that is Poisson lambda distributed, so what is the probability mass function of a Poisson distribution? In your script, if you have that digitally available, you might just look it up. Anyone?
UP is lambda and then the exponential minus lambda to the power of x. EXP minus lambda. Divided by x with
yeah. So that is the probability for a random variable, which is, let's call this random variable x, taking on the value x, small x. So the random variable is large x, and the random the value that it takes on is small x. That's given by lambda, which is this parameter to the power of x, times x, also the exponential of minus lambda divided by the factorial of x. That's just how it's defined. There's not that much to say about this. So this means then, of course, if this is a Poisson distributed, that in this case, just adapting things, we have lambda, our lambda ck u to the power of c, because we're asking about this little c here, times the exponential of minus lambda c larger than k u divided by the factorial of c. This is just writing out what it means that this random variable c larger than ku is distributed according to a Poisson distribution. And then the remaining question is what is the definition of this expectation parameter under RFP? Does anyone remember that? Or can anyone look that up?
Equal to the expectation parameter of
U. That's U, and that's the cluster forming threshold.
and then probability of k u larger or equal to small k.
Yep. So what does this KU model? That's the cluster volume. So that's the probability of general. So this is why I'm always saying this is kind of the expected probability, and that any cluster in the exclusion set takes on a volume small k. And in this case, of course, it's the probability that the volume that any cluster at this cluster defining threshold u takes on a value larger or equal to k. And this is, of course, here the number of clusters. And that's the expected number of clusters times the probability that any cluster has a volume larger than k. Yeah. Good. So this is actually this is really, really important if you want to understand the SPM table p-values, because this is essentially what is behind most of the p-values. Not all of them, but most of them. We will see that in a second. And that most of the p-values relate to this random variable. This was actually made explicit in this paper by Carl Friston and others in 1996, which I think is basically the only paper that relates to the SPM p-values as explicit as it gets. So one thing that is maybe helpful also in this regard is to talk about the distribution function or the cumulative mass function of this. So basically the question of what is the probability for this random variable CKU taking on values equal to or smaller than a given value, so cumulative distribution function. In the current section, I denote that a little bit different than in the general section in the very beginning, just to make the notation less complex. So remember that a cumulative mass function allocates to the values that the random variable can take a value in 0, 1, so it goes up to 1, and then it, for a probability mass function, the value that it takes is defined as the sum of values up to the value of interest. There's another small typo in the script. So again, you have to, so I'm bringing this up again and again, but you have to become familiar with it, because you need to, in this case, clearly be able to switch between density or mass functions and their cumulative density and mass functions. In this case, it's a mass function, and remember that what the cumulative density function plots is the probability for being smaller or equal to some value here. So if you, in this case, it's a mass function, if you have this C here, then what you have in the cumulative form is that you plot this area on the y-axis here. Yeah, so this is just something that you learned in undergrad statistics and psychology, because you all looked into the T distribution table to look up the p-value, but somehow it was not that explicitly communicated to you, maybe. And I'm just writing the cumulative function like this in the current section. If you go into the code of SPM, you will actually see that the majority of p-values that are evaluated, which is done by this SPM p, so it's the function SPM underscore p underscore RF for random field theory, that this uses the Poisson cumulative distribution function. Yeah, so this thing is really how SPM evaluates these p-values. And now you note it here like that. Good, so this was just revision of what we discussed already with a change in notation from Q to C. And now we want to discuss actually these p-values, finally. But first we need to establish some more notation and assumptions of what we're actually doing. Because this is, especially if you read the literature, this is always gets a little bit lost, and then you have multiple things that mean different things at different times, so the same symbol, and it gets all a little bit confusing. So I try to be fairly clear about this. So we're talking about this process of creating the SPM p-value table. So what are the assumptions? So first we assume that an SPM, so a statistical parametric map, has been obtained, which, if you remember what I did in the very beginning, I could click and select an spm.mat file, and an SPM has been obtained. And you know that an SPM is a three-dimensional 3D voxel map of statistical values. And to make this fairly explicit, of e.g. t values. Yeah. So for each voxel in your volume of interest, you have a t value. Yeah. You have a map of t values. You have many t values. You have 40,000 t values. Yeah. Which are evaluated based on a contrast of beta parameters and the variance estimate for your GLM of interest that you have formulated. Yeah. So that's the first thing. An SPM has been obtained. Second thing is that a cluster forming threshold or cluster defining threshold U tilde is defined or has been defined. Maybe we put it has been. And this you do when you select in this results manager by SPM. If you do this thing none or FWE, and then you enter, for example, 0.01 or 0.05. And this is already a little bit confusing because the cluster forming threshold, U, that's a real value. That's for example, a T value that then thresholds the T map. However, it is entered in SPM as a P value. Of course, you know from undergrad statistics that P and T values are kind of equivalent. So if you have, for example, here 0.05 as a P value, there is a corresponding critical T value, right? So what SPM does is that it takes this P value that you enter there and transforms it into the corresponding height threshold. This is what you see in the footer. So if you look at in the figure 7.1 SPM P value table, you see height threshold T equals 8.51 and P equals 0.000. Which is, I think, this family-wise error corrected 0.01. So what SPM does there is that if you select none, then it just actually uses the corresponding cumulative density function of your statistics. So if you have an F map, of course, it uses the F distribution. If you have a Z map, it uses the Z distribution. Most of the time you have a T map, so it uses the T distribution to evaluate the corresponding critical T value. And this critical T value is our cluster forming threshold. Yeah. If you select family-wise error corrected 0.05, it does something a little bit more funky, which is done by this SPM underscore UC function, which uses a while loop to evaluate family-wise error corrected height threshold. This is all very confusing because the only thing that happens there is that you define this cluster forming threshold U. Yeah, so the whole thing would be a lot less complex if it would just ask you about this cluster forming threshold U, and you would just evaluate, or you would just put in, for example, 3 or 4 or 5, which clearly relates to your T values. Yeah. So I've documented what this does. I haven't quite documented what this does in detail, but the important thing is you should not think about anything like family-wise error correction or p-values at this point. You should think, okay, I have a T-map. This T-map has T statistics, which vary from anything to, so usually they vary between, let's say, +10 and -10, and you define a U value, and this U value is, for example, 6 or something. Yeah, so this is what happens. It's just because they use this P value, it's just made more complex than it actually should be. The next, so this is happening at this point in a little bit of an indirect way, but it's just the case that this U value is defined, which then of course also allows SPM to evaluate the excursion set, because it can mask out everything, all the T values or statistics values that are smaller than this U tilde. What is also defined is, what you're also doing at that point is to define a cluster extent threshold. So this is where you're being asked how many voxels or something. And then it's always not really clear what this thing does that you enter there. So you enter K tilde. And as we will see later on, this K tilde has only is only meaningful or only has an influence on the set level p values, which nobody uses. Yeah. So in the left table, this p value that is there on the set level, this is directly influenced by this k, but nobody uses this set level p values. So for the p values that you then find in the literature, this k actually doesn't have an influence. What it influences in addition is that you get in the representation of the cluster volume, you get rid of smaller clusters. So for example, if you enter 100 or so, you will not see clusters smaller than 100 voxels. This will of course change which clusters are listed in your p-value table, but the p-values for the clusters that survive this in the cluster level tabulation is not affected. Yeah? So this is why it's not immediately clear what this cluster extent threshold does. It affects the p-value at the set level, but nobody's looking into that anyway. Good. So these two things you enter. And as I said, there's the SPMU function that takes care of this, the SPMUC, if you choose family-wise error, and I will write that up in a little bit more detail, what that exactly does. Good. So then the next thing that we assume that has been done is that the number of clusters C tilde U is in the excursion set E tilde U is evaluated. This just means that the T-map is thresholded, and then the question is which kind of voxels are connected. So it has to actually, the code goes over all the things that are in there and checks which voxels are connected and just form a cluster. This is also not completely trivial, so there are SPM functions that do that, like SPM cluster and SPM BW label. So this is of course related to how you define when things form a cluster, and Sebastian will happily tell you all about these connectivity schemes, like 26 connectivity schemes. This is something that we don't discuss in detail here, so we just assume because this is more like a numerical thing. So this is being done, but has nothing to do with probabilistic modeling. So we don't talk in details, but about this. But this is being done. Then the volumes of these clusters is assessed, and the volumes I call Ki. So tilde, so Ki is the volume of the ith cluster, and the clusters go from 1 to C tilde. They all have a tilde now because I want to make very explicit that these are the things that actually are evaluated in the scenario that you are defining the SPM table. Yeah. So there is this function. This is actually the volume evaluation of these clusters. This actually happens in the SPM table function, which I have rewritten. There's a function called SPM max, which does that. It's called SPM max because at the same time that it evaluates the cluster volume, it also evaluates for each of these clusters the maximum statistic in this cluster, and this I call Ti tilde. So the T is of course inspired by the fact that these are T values in a SPM T-map. It could also be a maximum F value or maximum Z value, but it needs to be very clear that this is something fundamentally different from the cluster forming threshold value. Yeah. So if you look into the SPM the SPM P value table, you see in peak level, so you see these clusters. So the way it's portrayed is that you always see these thick lines. this relates to the global maximum of a cluster. Yeah. So, for example, in this specific p-value table, you see T 15.70. That's in the cluster, which you can identify by clicking on it. So, which is located at -36, -86, -10 MNI coordinates, which is primary visual cortex in this case. This is the maximum, the global maximum in this cluster. There are, of course, other local maxima in this case, which SPM then reports for more than 8 millimeters apart or so, which is this 15.34 and 11.78. But actually for the p-values, the only thing that is important, specifically for the cluster corrected, the cluster level family-wise error corrected p-value, it's the maximum. Yeah. So this is also evaluated. This is this TI, and you see it in the table actually. And then, of course, what we assume is that the full width half maxima, so the smoothness, D, and the corresponding Riese volumes for D0, 1, 2, 3 have been estimated. This is actually done before you do this table, and you also find the report of that in the SPM table footer. So where it says full width half maximum, this is the estimated FD, and the Riese volume, it just reports for the entire, so it just reports R3, if I'm not mistaken. So, but it has evaluated all of them. How these things are estimated, this is left also for later in the course. But this has been evaluated, because otherwise one couldn't come up with these expected number of clusters and so on. So all of these things where you need the expected Euler characteristic, you need these things for it. Yeah. So is that everything? Yeah, so these are the assumptions. So be very clear about when we now talk about the SPM p-value table, that we are not talking about an arbitrary threshold U or an arbitrary cluster extent threshold K or some arbitrary cluster volumes. We are talking about the cluster volumes that actually relate to a specific statistical parametric map in a specific contrast, hence everywhere the tilde, and we need this tilde. Good. Questions about this? No. Good. Then let's take a break now, and then using this notation go into the SPM table and clarify what these things are.